Hi, we're going to look at one more slightly more challenging problem that deals with the um, Euler Totient function, the phi function. And this one is we're going to show that there's no integer n such that phi of n rather is 14. So think about what that means. That just means that there's no value of n where the numbers of relative primes between 0 and n minus 1 is 14. Okay. Um, and so again, kind of sketching out a proof here. We're not doing a full proof there, but just talk through what that looks like. So what I've done is and you should have seen this work in the book by now, but basically written out the full version of the phi function. So now what we're looking at is how does this work for composite functions? Well, any composite function that we can break down into prime factors, its prime factorization, essentially that's what this formula is giving us. So phi of whatever number that is, here's our prime factorization of that, is just going to be the resulting product of all those primes with one less power to each of those primes times one less than each of those primes. Okay, so for instance, if the prime here is 3, then it's going to be 3 to some power times 2. If this is 13, it's going to be 13 times some power times 12, and so on. Okay, so that's essentially what this formula is saying. Now, in order to show that there's no value of n such that phi sub n equals 14, one way to think about this is essentially what we want. We want phi of n, to be 2 times 7. Okay, so we're just taking 14 and rewriting it into its prime factorization. Which, I mean, to a certain degree, that makes sense because phi does have a bunch of primes in there. It also has numbers less than each of those primes, but it does have prime values in there as well. So essentially, by writing this and thinking back to stuff we've done already this year, what this implies to us is that 7 needs to divide the phi function. Okay, which obviously makes sense based on what we've done earlier this year with divisibility and so on. If a number equals 2 times some other number, then that other number divides the first number. So nothing too groundbreaking there. It does kind of imply two cases that we need to look at. Okay, the first case is what happens if 7 divides n? Okay, so n is the number we're looking at, so 7 divides n. Well, if that's the case, so if 7 divides n, that means that 7 is one of our prime numbers. P sub k. Okay, going back to this statement up here. So 7 has to be one of the prime numbers in there because we're essentially saying that it's dividing into this number right here. Okay. However, what this expression implies is that if 7 is p sub k for some k in the factorization of n, then 7 minus 1 equals 6 must also be a factor of phi sub n. In other words, we're saying that 6 has to divide phi sub n. But we've already shown right at this stage right here that phi sub n, we know what phi sub n is. Phi sub n is 2 times 7. there's no 6 there. So if 7 actually divides n, then 6 has to be present there when we calculate the phi of it. And so what we've reached here is a contradiction. Okay. So we have a contradiction if 7 divides n. Well, the other case is, well, what happens if 7 does not divide n? Well, let's think about what that means. Okay, if 7 does not divide n, then we're coming back up to, excuse me, if 7 doesn't divide n, then what that means is that at no point, I don't know why I just wrote that there, hold on. Let's go, if we think back up to this function up here again. If 7 doesn't divide n, then that means 7 is not one of the prime values that are over here. Okay? So 7 is not one of the primes that makes up n. Now, this actually leads to two contradictions. One of which then is, if we're saying that 7 divides the phi function, which is what we looked at up here, then since it can't be p1, p2 up through pk, then it must be p sub 1 minus 1 or p sub 2 minus 1 up through p sub k minus 1. But the only way that works is if we'd end up, so a prime minus 1 equaling 7 means that the prime would have to be 8. 8's not a prime. So there's our first contradiction. The second contradiction is the fact that it says 7 is not one of the primes that makes up n. But the problem here is that we know that, nope, one contradiction, sorry. It's a little bit late when I'm making this video. No, I was thinking of something else there. The contradiction we want is the one up here. So the only way that 7 could exist is if 7 was, then 7 must equal some p sub k minus 1, which implies that 8 equals some prime number, which is our contradiction. So what we've shown now is that we assumed that that there was some n value that worked, and so in writing it in this form, we said that 7 needs to divide that. And the only two cases, we basically said either 7 divides n or 7 doesn't divide n. And so that we've taken care of both situations there, and both of them lead to contradictions. So the only thing that must mean is that there is no value of n for which phi of n is 14. And there you go. And that's basically the way we would do that particular proof, going back to our proof by contradiction.